Hey, Alex. I've been hearing a lot about Japan and quantum computing, and I'm just so curious. What's really happening over there, especially with the latest breakthroughs?
Oh, Heidi, you've hit on something absolutely huge, right? Japan has just entered this incredible new phase, particularly with trapped ion qubits. Osaka University, they've really spearheaded a milestone. They've successfully demonstrated what we believe is the country's first automated, cloud-operated trapped ion qubit system. I mean, accessible over the internet. It's a pivotal shift in how they'll use, share, and expand quantum hardware in the coming years. It's truly, truly remarkable. A game changer, really.
Wow, accessible over the internet? That's wild. So, how does that even work? What exactly is this system, made of or doing?
Well, the Osaka University team, they got it operational around July 28th, 2025. It integrates a single ytterbium ion within a linear Paul trap. This ion species, it's highly valued for its extended coherence times and stable internal states, which is super important for quantum operations. The platform precisely cools, controls, and measures this ion using an intricate network of lasers, magnetic fields, microwave drives, and automated routines that continuously monitor system health. But the core innovation, the real kicker, is doing all that remotely via a cloud-based interface, leveraging this open-source OQ-TOPIS software stack.
Ah, Octopus and that cloud interface. So it's hands-free operation, you said. What does that practically mean for researchers trying to use this quantum computer?
Exactly, Heidi. It's totally hands-free. This automation means users can submit a quantum program online, and the system, it autonomously executes it. It performs tasks like checking for ion presence, reloading if necessary, aligning lasers, preparing the qubit, executing gate operations, collecting measurements, and just repeating that whole sequence without any manual intervention. This is a huge, huge advancement for ion trap systems, which traditionally required specialized personnel. I mean, Koichiro Miyanishi and Kenji Toyota, the professors, they've really pushed this, to alleviate that operational burden. They even demonstrated 1,000 consecutive remote runs of a single qubit rotation. Stable operation, even with some photon detection inefficiencies, it's incredible.
1,000 runs. That really speaks to the stability, doesn't it? But, they're only using a single qubit right now. How does that stack up against what we see globally with IonQ or Quantinium?
It's true, it's just a single qubit for this initial demo, and it's not attempting multi-qubit logic yet. But this lays a crucial foundation for future scaling. Globally, companies like IonQ and Quantinium are developing larger devices, exploring commercial applications, and they're recognized for their high-fidelity operations. This Osaka system, however, aims to alleviate the operational burden by automating critical workflows. So while it's smaller, it's proving the automated operational stability, which is just essential. They're seeing 94% fidelity in state preparation and measurement already, which is really strong for a first step.
Okay, so it's a foundational step, but a really robust one. I'm wondering, though, for researchers in Japan, how does this actually change things for them? Does it give them better access than before?
Oh, absolutely. This is huge for expanding access to quantum science within Japan itself. Before this, Japanese researchers often relied on international providers for hands-on experiments. Now, domestic access to a real qubit via the internet, that offers immediate benefits. Universities can incorporate the system into coursework, research groups without specialized optical setups can finally test circuits, and industry partners get domestic infrastructure for proof-of-concept workloads. It means users can concentrate on circuit design and data analysis rather than, fiddling with physical lab adjustments. It's really expected to accelerate progress just like it has with superconducting qubits.
That's fantastic. And you mentioned OQ-TOPIS earlier. That's the software, right? How important is that piece to this whole picture?
OQ-TOPIS is critical. It's an open-source software stack developed by Osaka University working with Fujitsu, systems engineering consultants, and TIS Inc. It launched on GitHub around March 23, 2025. It's essentially a comprehensive, customizable operating system for quantum computers. It lowers the barrier for deploying cloud-accessible quantum machines by offering a translation framework between cloud-submitted circuits and the physical control signals. It's creating a reproducible template for other Japanese ion trap projects, establishing a clear technical pathway for Japan's expansion. Fujitsu even plans to make it available for its research partners later this year.
Wow, so it's not just Osaka University, there's a broader ecosystem developing. What about other players in Japan, like beyond this collaboration? Who else is getting involved and what's their vision?
Oh, there's absolutely more to this story, Heidi. Qubit Core Inc., for instance, they spun off from OIST in July 2024, and they're developing their own distributed quantum computing systems leveraging trapped ion tech with micro-optical resonators. They're aiming for Japan's first commercial deployment of trapped ion quantum computers, with a roadmap to unveil a testbed for quantum error correction in 2028 and a system demonstrating scalability to over 1,000 qubits by 2029, targeting commercial deployment by 2030. And then there's the Toyota Group, which is also deeply involved. Toyota Tsusho partnered with IonQ to distribute their solutions across Japanese industries, and Toyota Motors Frontier Research Center has been doing applied quantum research since 2021. It's a huge collaborative push, truly aligning with Japan's Moonshot R&D program, aiming for a fault-tolerant universal quantum computer by 2050. It's a really exciting, really promising roadmap.